So now that you've talked about how to use length-based models and you cleaned up the process from the process, we're ready to tackle the next approach. So for our approach, we're looking at how to construct a plan. And this time we're going to focus on graphic organizers. Now, this is not as invasive. This is more of a preparation that will go and support our explicit instruction. The first graphic organizer that I want you to think about is a clues and undos. And there are other ones out there, but let's focus here. A clues and undos is simply a way of helping a child examine what's occurring in the equation and then setting up an approach to it. So we don't even have to do the computation at first. We just want to set up the logical approach. So in this case, 5 sixths times x plus 4 equals 8. So what's happening to x on that side of the equation, right? In that expression, 5 6x plus 4, what's happening to it? Well, the first thing that's happening close to x is it's being multiplied by 5 sixths. Good. Then what happens to it? We're adding 4 to it on that side. Okay, so it's being multiplied by 5 6, and then we're adding 4. How do you undo it? And follow my mouse here. How do you undo it? We need to subtract both sides by 4 and then multiply both sides by its reciprocal, 6/5. Yes, if you want to say divide by 5 6, I'm with you. But follow me here. I want to subtract 4 from both sides, right? Additive inverse. And that gives me 5 6x equals 4. Then multiply each side by 6/5, the multiplicative inverse. What am I left with? 24/5. X is equal to 24/5. Clues and undos is just another graphic organizer that's out there. And it's not going to teach the students by itself, but we can use it to help our students identify the additive and multiplicative inverse and even set the organization for what we're going to do first, right? And so you do that proximo distal look of what's happening to x closest, and you move out into that whole expression. Okay, let's hit that last one, the cognitive strategy. Now, cognitive strategies are taking a task analysis and putting a term to it and teaching it at that term. It's not just saying, here's isolate, put it up on a board and say, good luck, look at did you read the poster? Right? No, we're actually going to teach them isolate. So the cognitive strategy that we've seen used in another research project was isolate. Isolate was identify the variable to be solved. You could even have, I think they even had their finger pointed on it. They were using a manipulative, so they identified it with that manipulative. Set up the calculations to isolate that variable. You probably can even think here, I could use the graphic organizer for that. You got it. Organize the calculations to balance across the equal sign. List those calculations to happen in the same order on both sides. Answer calculations on the variable side, answer calculations or total, calculations on the other side, then evaluate the reasonableness of the answer. Isolate is just a task analysis we've all taken. When we approach when we approach solving equations, it's just putting a name to it, using verbs to push the student actions. Now, when you're going through those steps, you can actually look at all the same approaches we did, right? So in this case, it's 4x minus 2y equals 8. We're solving for y. So we want to know what is y. So what do? We set up the calculations, right? What do I need to do for it? In this case, what's happening to it? It's being multiplied by -2, then I'm adding 4x. So let's do the reverse of that. Subtract 4x from both sides, right? And what are we left with? 2x equals 8 minus 4x. Then we're going to do the multiplicative inverse. We're going to divide both sides, all terms, by -2. Now we're left with 1y is equal to -4 plus 2x. So we check for reasonableness of this. Does it make sense that 2 times -4 plus 2x would help finish this out? You actually can plug that right in, teach substitution, change colors, make this one color, match it into y, this color distributed property, and show how it computes back to the, right? It computes back to the original. But the purpose of this is to help our students understand the steps to solving for an unknown and seeing what happens when we get to an answer. So when we're putting this back in and we're trying to say, well, could both sides of the equation actually equal 8 if I plug in -4 plus 2x into y? The answer is going to be yes. All right, another look at this is using the order of operations to simplify your expression, and then using the same approach we talked about earlier, that reverse order, to solve for it. So if you're given something complex, such as 3 times the quantity 2x plus 4 equals 7 squared. That's when I was, oh my gosh, so I don't even know where to start with x here. Okay, so it's a little over complex. Let's use the order of operations and see what we can simplify, and then we'll solve for x. So in this case, parentheses. I do have parentheses. Inside them is 2x plus x. Solve what's inside the parentheses. Okay, it's 3x. All right, so now it's 3 times 3x plus 4 equals 7 squared. Are there exponents here? Yes. So 7 squared would be 49. Great. Now I have 3 times 3x plus 4 equals 49. Okay, multiplication. 3 times 3x would be 9x. Now I have 9x plus 4 equals 49. Stop. Yes, there is an addition, but it doesn't help simplify things here, right? Because on the same sides of the equation. However, we have used the order of operations at this point to start to simplify, one, the expression and that exponent, right? That constant. So what we now can do is now we can switch modes and solve for the equation, so that 9x plus 4 equals 49, and we can go through there. Additive inverse, multiplicative inverse. But again, we can simplify the equation by expression through order of operations. The purpose of this is when you set up your construction or your plan, you want to have that plan be solid so that the students know what they're doing. And then you can lead through modeling. Different variations you could do here. One, you can teach by steps and share your reasoning consistently. That is one great approach for this. Another plan might be you're going to scaffold complexity as students develop. In other words, I'm going to build in more computational complexity. Maybe I'll even build in more variable complexity as my students learn this. But I want to start simple, build up their confidence, get a streamlined approach, and then building complexity as they grow. The choice is yours. Remember, some students are ready for the fast track. Other students will need you to scaffold consistently and build up. So let's talk about some of that scaffolding complexity. You can see that when we're starting to scaffold, think, right, start on the left, go down, and then we'll circle back up here. So we start out with just, it's a computation, right? In this case, x would equal, right, -2. Then I need an additive inverse. Then I would need an additive and a multiplicative inverse. Now my coefficient starts becoming a little uglier. In this case, I got a fraction. Maybe I'm adding the distributive property in. Maybe I'm adding fractions and the distributive property in, and I'll even put in an exponent for good measure. As we're working through and they start getting down and they're able to understand one variable, right? We said, right, building complexity of computation. The next step would be building the complexity by adding more complexity of variables. In this case, I add in another variable. Then that variable increases the computation around it. Maybe I'm adding that variable and I'm adding in power. My point is that we can slowly build in our students' knowledge so that they can do better through the process. This instructional momentum, this gaining momentum idea, is showing them what to do first and building in small step by small step. The strength of this is we build student knowledge in incrementally over time, and we're able to take them to a level of mastery. And we know when to slow down and when to speed up. The weakness is time. A lot of people think they don't have the time for this, so they just jump in and they jump in 2 feet into the complexity. And then you have students who are overwhelmed at this and think they can't do it. Know your students and know what levels they can handle. To be more fair or judicious, take your time and do slow steps. Okay, we've led by modeling. We're having a scaffolded approach. Now it's time to talk to engage in guided practice. I want to engage in them practice with me and with each other. So I'm going to start at some problems at their medium to hard complexity. I want them to analyze examples, analyze problems, and see what's happening. As they grow in this level of complexity, I want them to start laying out a plan. I want them to see for these medium to hard complexity problems a couple steps at a time. What would you do? Why would you do it? I don't even want to see the computation. I want to hear the reasoning. As they build that reasoning, we'll get even more difficult. and I want them to start checking their accuracy. Now I want to see your computation. Now I want to make sure you can do this. Do the next 4 problems on your own. Do the next 3 problems on your own, and I'm going to stop and check. This, turn to your partner, turn to in your group, in your triad. This growing complexity helps build our student up so that they can get to a point of independence, and they can even allow us to move around and give our work so we can rotate over. When some students are at this independent level, allows me to come back a level and work with students here. But the idea is we can build complexity as far as the computation. We can build complexity as far as the variable use. We can also build complexity as far as individual student accountability. As they apply these things independently, again, try 4 problems on your own. Check with your students' understanding when you walk around. So in other words, if I'm at 4 problems independently, I don't want to run around because of learned helplessness. I may say, stop, show me write your answer on a board, 2 hands on board, board to forehead, show me what you're doing. And then I get to talk with them about what's happening. And then we start building in more complexity, including more word problems. Word problems can be everywhere, but I might include more word problems that force them to really think about the work. And then I can even finally interleave other types of problems, which means problems from old work we've done that they may have forgotten. Once they get to that level of complexity and they're able to analyze the problem, make sense of it, start putting in different types of problems in there to make sure they're still looking at the problem, not just robotically going through it. Your turn. Look back at what we talked about. What's the benefit of a graphic organizer and or cognitive strategy that we use to teach multi-step problem solving? Were they helpful, and what can you do to incorporate those in your classroom?